and how we can use such protocols to communicate with some network devices. And then during the second half, we'll focus more on the test automation principles and go through a couple of examples. Also have a hands-on exercise on how to write some simple test scripts that can help us automate our testing procedures. These are the topics for today. So we will be starting in about 1 or 2 minutes, since we see that more people are still joining. So stay tuned. And the first one to open today's training is one of our young engineers, who is behind most of our communication protocols implemented in the Typhoon HIL environment. Thank you very much.
Hello everyone, my name is Typhoon, and I'm working here at Typhoon HIL as an embedded software engineer for previous 2 years. And my main field of expertise is signal processing with toolbox and this communication protocol toolbox that I will demonstrate today. So basically, in this presentation is about communication protocol that we implemented in Typhoon HIL toolchain. And during this presentation, a short overview of each implemented protocol that we presented, as well as how these protocols are configured and how they work in Typhoon HIL. So let's start. So first, let's see what communication protocols are implemented in Typhoon HIL toolchain. So first we have Modbus TCP, GOOSE protocol, which is a protocol from the IEC 61850 standard. We have variable exchange protocol and the CAN bus protocol. We will give a short theoretical introduction for each protocol and show you how it's implemented and how it's configured for every protocol. So first, let's start with Modbus TCP. Modbus TCP is an industrial communication protocol. As the name suggests, TCP means that it's using a TCP IP protocol to communicate. Also, there is a TCP RTU protocol that will communicate through a serial interface, RS-232 or RS-485. But at this time, only TCP in our full chain. Master slave protocol, which means that the master will initiate communication slave device, and the slave device only will respond to these requests and cannot communicate communication on the master solution. And the TCP roles are not used as much the common terms are client and server. So master device becomes client and then slave becomes the server. Both slave and master devices are implemented in skill. Slave device visible to this present point, it's not critical. And if you want on skill 42 and skill 64. Or client device. And Modbus API. And this Modbus. Modbus protocol principle behind Modbus protocol is registers. Everything is defined with registers. Protocol defines 4 types of registers.
Plastic channels.
Registers. And difference between these registers are presented here in this table. We have discrete input, control, output, type, boundary, registers, and moving register with 16-bit. And we have read-only, read-write registers, where discrete input and discrete registers. In Modbus are basically on this object. Again, we see that only 16-bit registers are represented existing Modbus TCP or Modbus platform. But there is a mechanism to represent the 2-bit and 64-bit values by combining 2 or 4. Modbus TCP has a lot of functions. It can be the only functions that are implemented in this here. The set of increments. We have functions for 1-bit access and functions for 16-bit access. We have basic read and write functions for registers and for Modbus Server is implemented.
Hello.
First, Modbus device again is implemented as an accessing component, and it is straightforward tool and support. This facilitates their own processor and Linux operating system running for them. This is how the component looks like in schematic editor, and it can be found under the communication tab, Modbus device. We see that it has a coil, discrete folding and register inputs, and only coil and folding outputs. This is because the coils and folding registers are read-write, so the read procedure is done through this input terminals. So every signal that is connected to this terminal is read to the client, and again, if you want to write value, that value will be shown here on the output. On double-clicking the component, the dialog window will open. Here is how it looks, and we can see that there are two properties: the Modbus configuration and the execution rate. The Modbus configuration is basically how you configure the server, the communication part and the register part, whereas the execution rate is basically single processing execution rate. Again, there is another button, configuration preview, that shows you the configuration in table form, easier to read once the model is compiled. We will show this in the demonstration later on. So configuration is basically defined through Python dictionary, and here is in the description you can see how it should look like. There are a number of fields defined in the configuration, as you can see here. So we have the communication parameters like port, IP address, net mask, and site ID that we define, and the register parameters, for example, core addresses, call output addresses, discrete addresses, folding register, basically all register addresses can be defined. The best way to configure the server is to use model initialization. In model initialization to basically write the configuration and that parameter put into property of the Modbus. Again, it's Python dictionary type, and here you can see example of configuration. So we have the network, the communication part, port, IP, net mask, and site ID, and the register part. And registers are defined basically by addresses for like a list of values of addresses for 12, like 0, 1, 2, 3, 4, and discrete input again. And for polling and input registers that are 16-bit, the values are somewhat different, meaning that you can group 2 or 4 addresses with these square brackets to represent one 32-bit or 64-bit register. Again, you can also specify the type of the registers. For example, you can specify the unsigned, integer, and floating type. So here in this configuration, we have a 16-bit unsigned register, 16-bit integer register, 32-bit unsigned integer and float registers, and again 64-bit unsigned integer and float registers. And also applies for the registers. So one good thing about this way that the server is implemented is multiple server configurations can exist in one Typhoon HIL device. So you can specify a number of configurations, number of servers that all run on one 142 or 164 device, and each of these servers can have its very own IP address. So again, it's only one hardware device, but with multiple IP addresses. So looking from the outside, it looks like they're working with number of devices, number of layers, but all it's one device. And how it looks like, you can see it here. We specified 2 configurations that are basically the same except for IP address that are different in the last characters. Modbus Client implementation again is through Modbus API from SCADA, and it uses PC to communicate. It doesn't work through HIL device. It works through PC. So a PC must connect to the network to enable the Modbus Client implementation. And what this means, it means that it works on any HIL and virtual HIL device. Basically, it works on PC, but you need to have some model compiled and running to enable Modbus Client to run SCADA. So this model can work on any HIL device plus virtual HIL device, whereas Modbus only works on real hardware. Through Modbus API, there is support for standard read and write functions, support for advanced read and write functions, and some additional functions for conversion, which we'll explain next. So standard functions, basically standard function defined by Modbus protocol for reading and writing the values of registers. Again, 1-bit and 16-bit access. An example for this is reading the registers, where you specify the starting address and the number of registers you want to read. And for write multiple registers, you again specify the start address and the list of values that you want to write. Advanced functions. The advanced functions are presented for 16-bit registers, and you have the read input register advanced, read polling register advanced, and write register advanced functions. And what this function makes advanced is that how you specify what register address that you want to read or write. So basically, the syntax is exactly the same as server configuration, where you specify the list of registers, the list of addresses, and group them based on the length and the type of register, and you can this string you can put in the function argument and just specify the values that you want to write. So in this way, you can really write the whole configuration of a server. Additional functions. These functions are basically helper functions that help you for conversions, like conversion from one type to another. For example, one side 16 to N16, or float to one side 32-bit values. And there are functions to convert to list of values. For example, if you have double value specified in the model, you can convert it to list of unsigned 16 integer, unsigned values of 16-bit long list that can be written to a server. And again, convert from lists to from list of values. If you read, for example, four registers and get a list of values, you can convert it to integer 64. Okay, so next protocol that we have implemented is GOOSE protocol from the IEC 61850 standard. So a short overview of IEC 61850 standard is that it's used for communication between devices IDs from different vendors, and it's used in substation operation. The protocol with standard is standardized names and structure of substation elements. It's object-oriented and uses SCL or substation configuration language for describing the subsystems and the element of the subsystem. And it implements multiple protocols like MMS, GOOSE, GSSE, or SV protocols. Here is an overview of object how devices is represented in the IEC 61850 standard. So we have multiple layers. The first layer, the most abstract, is physical device, which is basically hardware, physical hardware, which is it consists of a logical device, and each physical device can have one or more logical devices. It's mostly one, and logical device consists of logical nodes. These logical nodes represent one function that ID can a function that is implemented inside the ID. For example, so here we can see a circuit breaker function and a measurement function. And these logical nodes here consist of data objects and data attributes. For example, this circuit breaker has a data object of position, which has attributes of state value, quality, and time step. And for this measurement logical node, we have total watts with magnitude, quality, and time step data attributes. And standardizing this structure and device names and node names, object names, attribute names is the primary goal of IEC 61850. And all this is done through this SCL notation. This SCL or configuration language is XML based, and there are different file types based on substation level. So we have an ICD file that is ID capability description, SSD file, system specification description, or SCD files, substation configuration descriptions. And these files are important, and we'll see in a minute why these files are important. So GOOSE protocol, as I said, is the only protocol implemented in Typhoon HIL from this standard, and it stands for Generic Object-Oriented Substation Event. It's used to communicate between IDs in the substation, and it is publisher-subscribe based. What this means is that one device is a publisher, and it publishes a message under some topic, where a subscriber can can subscribe to that topic and filter out all the other messages. So only the messages that that have the same topic will be filtered out and parsed. It is Ethernet based in local area network and event driven. Basically, what this means is the messages are sent periodically at some specified time. For example, every half a minute. And when an event happens, the burst of messages will be transmitted through the line, and this sending period will increase till it gets to again one half a minute sending period. So on every event, there is a burst of messages, and the period increases gradually. And in every GOOSE message, data set is transmitted. And what data set is basically a set of attribute values that are sent in a message. For example, if we go back to this picture, and data set can be, for example, only state value here, or it can be state value, quality, and time step together, or we can combine from the two logical nodes and say that state value and magnitude from different nodes are one data set. Okay, so how this is implemented in our toolchain is that we have two components: GOOSE publisher and GOOSE subscriber. And GOOSE publisher can be found under communication IC 61850 GOOSE publisher tab. And on double clicking, we get this this configuration window where you can specify the publisher parameters. Sorry. Again, I said that those SCL or configuration files are important, and here we see why. Basically, how you configure the GOOSE publisher is based on those files. You can choose any configuration file that you wish imported. That file is parsed, and you can select ID that you want to simulate and GOOSE control block that you want to simulate. For example, how it looks, we can see here. If we choose this Typhoon HIL server SD, we get two servers, two IDs, LD and ID. And for LD ID, we have this control box that we can select and simulate to GOOSE publisher. And this is a snippet of the SCL file, where we see here these values specified for GOOSE control box, and every GOOSE control box is basically attached to one data set. Similar is for GOOSE subscriber. The dialog windows is basically the same, except for the GOOSE control block, you specify the data set that you want to subscribe to. Again, we can see this how it works here, where we select what data set is parsed, and again a snippet, and we can see this data set we found here in the SCL file, where, for example, this data set test has data attributes general and quality in a data set. Okay, so going to the next protocol is variable exchange. This is not a standard protocol. This is something implemented to Typhoon HIL, but it's a simple protocol for sending variables over TCP and IP or UDP. It's server client-based application. It's really easy to understand and use, and as for now, it is only protocol with deterministic execution rate, meaning that if you specify that the message is sent periodically on, for example, 100 milliseconds, there's a guarantee that messages will be sent in that period. In Modbus protocol, the messages are sent only on the request of clients, which can be which are non-deterministic. And in GOOSE protocol, the messages are sent basically on events. And here we have deterministic as usual weights as what you specified. And variable exchange works for any HIL device. The protocol, as I said, is really easy to understand, and here is how it looks like. Basically, you have a TCP IP header and the variables, the values of signals, basically packed together in a TCP header. None other information is transmitted to these messages, only 32-bit values. So this means that the packing and unpacking of these messages are really simple, and it means that any external device that is programmable can implement this variable exchange protocol and communicate with the Typhoon device. This is how it is implemented in toolchain. We have this under communication Ethernet variable exchange, and we have this component setup, with which you can basically configure IP addresses of all the devices that are connected to your PC. We have variable exchange receive component used for receiving messages, and you can specify number of data that is in a message, what type of data it is, protocol, MDMS, port, etc. And variable exchange send, with which you can send the messages and set up the protocol that you want, the MDNS, the destination IP code, and so on and so on. So it's basically really simple to set up and really simple to use protocol. Next, CAN bus protocol. CAN bus stands for Controller Area Network. CAN or CAN bus are the synonyms. It's two-wired bidirectional serial communication. Multi-master protocol, meaning that any node can initiate communication, and each node in the network must operate at the same bit rate. And again, at least two nodes must be present in the network for it to work. CAN bus messages are really lightweight, only ranging from 0 to 8 bytes of data. And each message has a unique ID, which is used for priority, arbitration, and filtering of the messages. There are two standards exist, two variants of a standard exist. There is a CAN 2.0A, which has a 9-bit identifier, and 2.0B, which has a 29-bit identifier. Inside in our toolchain, only HIL64 can implement CAN communication because dedicated hardware CAN controllers must exist in a Typhoon HIL device to communicate, and only HIL604 at this moment has CAN controllers, and each HIL has two CAN controllers with a standard 9PND sub-connector. Both CAN A and B are supported, and at this moment no remote frames are supported in our implementation. And again, as like variable exchange, this protocol also has deterministic execution rate. Similar to the variable exchange, there exists a CAN setup component located at communication CAN bus tab. From where you can specify for each HIL, you can specify the baud rate and execution rate of each controller. CAN send component where you can specify one message to be sent. Where you see at the top, you can specify on which controller do you want to send the message, identify type, value, message length, and distribution type, where it can be periodically or event. And you can specify how you back the message. Basically, multiple signals from a simulation can be backed inside one can message, and this specifies the rule where you put a start bit and length bits for each value. Can receive component similar to can send, only there is no sending configuration. You specify how you unpack the message. So what signal is on what bit and what length. And you can specify for which controller you want to read the message and identify type and so on. So to recap, what protocols are implemented in the Typhoon HIL toolchain: Modbus TCP, GOOSE, CAN bus, and exchange protocols, where Modbus TCP, GOOSE, and variable exchange are Ethernet based, whereas CAN bus requires additional hardware and CAN controllers to enable communication. And only variable exchange and CAN bus have deterministic execution rates. Depending on what HIL do you use, for example, a variable exchange can run on all HIL devices. Modbus Server and GOOSE protocols can run on HIL 4.604 devices, whereas Modbus Client can run on all HIL devices and virtual HIL. Again, just to mention, it runs on PC, not actual HIL device, so any HIL can support this client. And CAN bus only works with HIL 604. There are many more protocols out there, industrial protocols that are in use today, and more protocols are still to come in our toolchain. And at this moment, there is a plan for implementing the DNP3 protocol, CAN open, and SV or central values protocol beside the IC 61850 standard. So if you have any questions, feel free to ask them now, and I'll try to answer as many as I can. And after the break, we'll have a demonstration on some of the protocols that I mentioned, so you can see how that actually works. Yes, please.
कौन सा सेंटर का एक सेंटर में ओपन करके आप तो चले गए, हम सब वहाँ वो कर रहे हैं गुरु मैंने कॉल किया फिर उनको, फिर मैंने कॉल करके बताया हम यहाँ ट्राई कर रहे थे, वो नीचे था तो उसको म्यूट नहीं कर पाए। म्यूट कैसे करना था उसको? तो यहाँ ही म्यूट का ऑप्शन है, बट 18 वाला बहुत सबसे नीचे था, सो कैसे फिर कैसे ऊपर लेके आएंगे? उनको राइट क्लिक कर दिया, उनकी स्क्रीन यहाँ आ गई, फिर मैंने सोचा उनको छोड़ा।
So Modbus TCP, GOOSE, CAN bus, and variable exchange protocols are implemented. Ethernet-based protocols are Modbus TCP, GOOSE, and variable exchange, whereas CAN bus requires additional hardware, the CAN controllers. And deterministic execution rates are achieved through variable exchange and CAN bus protocols, and the HILs that each protocols work on are shown below, where variable exchange can work on all HILs, Modbus Server and GOOSE can work on HIL 402 and HIL 604. Modbus Client can work on all HILs and virtual HIL, and CAN bus can work on only on HIL 604. So just to make it clear, none protocol is works on virtual HIL except the Modbus Client.
Like for example, additional hardware display cameras. PDF वगैरह
Okay, so basically there are no more questions left, and I'll just announce a 15-minute break, and then when we come back, I'll show a demonstration of these protocols, some of these protocols, and you can see how it works in the healthcare tool chain and with real hardware devices. Thank you.
So 2, 3 check the number of hardware जब use करेंगे
Hello.
successful.
Do you have any problem? उन्होंने simply on किया है
communication protocol presentation, and it's about demonstration how this works in real life. So we will see a demonstration for Modbus Server, Modbus Client, and GOOSE publisher and subscriber protocols. First, let's see what was the setup. So in this setup, we have a HIL 604 device here. HIL Connect, this big box underneath. IDF 650 relay from ABB located here. Backup PLC here, and they are connected with this Ethernet switch and LAN cables. So first, a Modbus Server demonstration. We'll for this demonstration, HIL 604 will be a server, Modbus Server, and we will use an external Modbus client called Pure Modmaster, from which we will control and read the values of the simulation. And as I said, they are connected through Ethernet switch. So let's see how that looks in a schematic. Okay, so we have a Modbus component here, and we have the inputs to the component that are represented as SCADA inputs, which we can control from simulation. And there are codes to read for output and for inputs. If we go into the Modbus component, we can see these two parameters, the value of these two parameters, and let's see what the configuration is. If you go in model initialization, you can see how those are it. We can see the configuration of the Modbus. So we have port 502, IP address of 192.168.0.210, and the value of addresses of each registers. Okay. Once the model is compiled, we'll run the simulation. While the configuration is compiling, we can see the configuration preview, as I mentioned, in the template form with communication part and register map part. Right. I'll just go quickly back, explain it here. And you can see the input for Modbus device, which coral is for which Modbus input, the length in bits, type of register, and address. If we go down to the input registers, you can see type of unsigned integer, float, and the 32-bit, 64-bit, 16-bit registers, and all the addresses. Okay, so in Modbus SCADA, we will load the console control panel, where we can control and read the values from the registers. We will control the core values with these checkboxes. I'll just lock it, and monitor the calls with these LEDs. And for the registers, we will control the values with sliders and with display boxes. Okay, so first I'll just run the Pure Modmaster program. I'll just put it side by side so you can see everything. Okay, so if we run the simulation, we can connect with this. If we specify the Modbus TCP, IP address as is defined in the server, we can connect to the device and read calls. If we read calls for static address 1, read 5 calls, we can control these values with this SCADA input. So as I change the values of the column boxes or checkboxes, you can see how the Modbus master reads. We can control the values of the simulation using write coil. Of 100, 5 coils, and just the values specified here will show on these LEDs. So if I write 1 here, the LEDs will light up. And that's how we control the simulations. For the holding registers, we can again read holding registers from starting at 0, 20 of them. And by changing the value of the sliders, we see the change in Modbus Master. So first register is unsigned, second is integer. If we go in the minus, we can see that this Modbus Master doesn't represent the minus, only the, if we go to the hexadecimal representation, this is basically this value representing the hexadecimal. If we look at 32-bit values, if we change the value of 2 register will be changed. And again, changing the 64-bit register, 4 register will change. Write multiple registers from address 100. If I change the value here, you can see the change in the simulation. For example, 52. Because this is a let's switch back to decimal representation. And the value that I write will be shown here. I can write 65535, which is -1 in integer, and it will show -1. And for example, this value of 32-bit integer, starting from here, if I write 1, it will be 1. If I write in the upper half of register 1, it will increase. It will combine these 2 registers and represent one integer value. Okay, so next. Just a moment. Okay. Next is a Modbus Client demonstration. For this demonstration, we use Typhoon HIL SCADA as a client, and we use backup PLC as a server. They are both connected through Ethernet switch, and here we see the backup PLC. We have a terminal controller, digital input terminal, digital output terminal, analog output terminal, and analog input terminal, as you can see here on the screen. Okay, so for the demonstration, as I mentioned, any model can be used to. You need basically a model to run in SCADA to enable the Modbus API. So this is a simple example of some SCADA inputs and probes that are compiled and run the client through SCADA. I'll show you how to configure the client here. I just load the UI panel. Okay, so in the SCADA initialization, you specify what host address you want to connect to and the port, and then open the Modbus client. These are some helper variables that are used in the SCADA, but this is the most important part. With this function, you open the connection to the client. These 2 widgets are used to read registers and write registers. For example, in read register, the read input register functions is called to read the digital inputs and to read the analog inputs from the PLC. And in write register, write multiple registers and write single register functions are called to write analog values and digital values. And inside these widgets, only the values read are scaled and displayed. And sliders, the set value is scaled and then written to the right analog values, which are written to the PLC. So let's start the simulation and see how it works. Okay, so it didn't apply the initial values. So basically, changing this digital input. I won't mention how the PLC inputs and outputs are connected. I'll just show it. So basically, analog outputs are connected directly to analog inputs. As I say, digital outputs are connected directly to digital inputs. So the values that are written from the client will be read from Modbus from the client. So changing these values will automatically update these LEDs, and changing of these sliders will automatically change the values read. So, and also for digital inputs, if you watch these LEDs on the PLC hardware, you can see the change. So yeah, you can see the change in LEDs both on digital outputs and digital inputs. And again, by changing the value of analog inputs, we can read those values from the digital inputs. And last but not least, GOOSE demonstration. So for a GOOSE demonstration, we use publisher and subscriber blocks on HIL 604 and use ABB feeder relay 615 to communicate to. Also connected to Ethernet switch. Here's how the relay is. And for REP 615, overcurrent protection is implemented, which will react for currents larger than 110 amps. Overvoltage protection, which will react for voltages over the 13.2 kilovolts. And the supervision is implemented. Basically, supervision is sent from HIL to the relay. If the supervision is on, the overvoltage protection will not work. If the supervision is off, the voltage protection will work. So, I'll just show the model. Here's the model. In the model, there are two generators. One is a grid forming generator, another is on the other side of the circuit breaker. And the circuit breaker will close automatically if the generators are in sync. The sync check is done internally through this signal processing circuit. And we have here a relay that is connected to the grid, and basically a variable load that is connected to the grid through the relay. And the relay is basically just represented as measurements that are sent to the real hardware, the voltages and currents, and 0 voltage, 0 current. And the relay will really controls the circuit breaker through GOOSE here. And we see here that by importing this SCD file, we can select which ID we want to subscribe to, and we want to try to relay the overcurrent protection. If we see the data preview, we can see the three attributes here: general, quality, and timestamp. Again, for the lower subscriber, we subscribe to over voltage dataset, which also has general, quality, and timestamp. We use this general signal to basically, if any of the two protection works, the relay will, the controller will turn off. Not controller, but contactor. And we have this supervisory block, which is basically a GOOSE publisher and a SCADA input. And with this GOOSE publisher, we send the supervision control and supervision signal, which turns off and turns on the over voltage protection. Just to clarify, the HIL Connect device, the big box underneath the 604, is used as an amplifier to amplify the signals from the HIL device so that they are in range for the relay to work correctly. So the HIL Connect has a high voltage and high current outputs, high current ranging from -10 to 10 amps, and high voltage ranging from 180 to -180 volts, and are connected to the relay, and also the LAN cable is connected to the relay that communicates with GOOSE. So if you load the simulation, we can demonstrate this functionality. Okay. So once the module is loaded, I'll just load the custom UI panel and settings file to configure all the digital and analog outputs. So this is a custom UI panel. This upper part, we will not concentrate on this, only the lower part. So basically, if we run the simulation, the automatic sync control will be active, and once the generators are in sync, the circuit breaker will close, and then we'll turn on the variable load. So this lower part of the rig controls control of the circuit breaker. So we have a voltage measurement, current measurement. We can set the current for the variable load. We can turn it on and off, and we have these widgets for controlling the supervision and reading the over voltage and lower current protection, and then reset the relay if we need it. So as you can see from this widget, the generators are in sync, circuit breaker is closed, and now we can close the contactor of variable load and set the amps. I don't know if you can see it, but this 20 amps is shown here on the relay. First three values for three currents, so 20.6, and underneath there are three values for voltages that read 11.47 kilovolts. So if we increase the amps, the values values on the relay will increase as well. And again, if you increase above the 110 amps, the trip is ready, and it will trip after 3 seconds. If we reset the relay and not go back to the current, the relay will trip again. If we decrease the current, we can reset the relay, and it will work fine. So with the supervision button, we can set the GOOSE command to enable the supervision and disable the overvoltage protection. If I click this button, this LED will light up. It says that supervision. And if I increase the voltage now, so that the RMS value is above 13.2, you can see this blinking LED, which means that the overvoltage will not occur. If I disable the supervision, after 4 seconds, the overvoltage will occur and this LED will light up. So I will disable the supervision. We'll just wait. Here, the overvoltages occur and the contactor is closed. If we enable the supervision again, we can reset the relay and the supervision will work and it won't get the overvoltage. Okay, so that concludes our demonstration of the communication protocols. If you have any questions, feel free to ask. We have a couple of minutes on our hands, so maybe I can answer the questions directly here. If you have some questions that will not be answered now, they will be answered in the QA after.
Modbus ये सब में यूज करते हैं, ऐसे बोला ना, ऑल HIL में यूज करते हैं इसलिए
वो भी कर देते हैं
मल्टीपल डिवाइस क्या है वेरिएबल
वो सारों में यूज कर रहा
वो
हूँ
भी सारों में यूज करते हैं. तो यही करना चाहता है ना कि
Okay, so there are no questions, and I'll just announce our new presenter, my colleague Ogin Bergitsa. He will be talking about test automation, and he'll be here in basically 5 minutes. So please welcome him. Okay.
an application engineer at Typhoon HIL. In this lecture, we will be talking about Typhoon HIL test automation, how to write tests using Typhoon HIL API wizard, as well as how to do regression testing. We will talk about API documentation, and this is the plan for today. And for tomorrow, we will see test suite in action, which is test automation combined with industry standards for pre-certification of power electronics equipment. So we will begin by an introductory presentations on how to write automated tests. In some of our previous videos, you have seen how can you make the work, how can you make the HIL work for you. And now the next step is basically making HIL work instead of you. For that, you need to learn how to utilize test automation. So, this is usual controller hardware in the loop test bench. We have the controller, the virtual plant inside a HIL. And as far as test is concerned, we have some test script elements, which are the stimulus, data capture, data analysis, and results recording. Of course, we also can automate the procedure even further, including loading the model in schematic editor, as well as compiling the model and then loading it to HIL. Basically, completely transferring your mindset from manual testing into automated testing. These are some general guidelines for test automation. Obviously, we need to define a scope of each test. It's recommended that for each separate feature or function, you do a separate test. And ideally, you want to aim for unsupervised testing. Today, we will see both semi-automated and fully automated or unsupervised testing. The test acceptance criteria should be clearly defined. So for every case, you should be aiming for pass-fail criteria, so just to make it clear. And the test should support standalone runs as well as batch testing. Something that we use quite often in Typhoon HIL is regression testing. It's widely used in software development, and if we would choose a sentence how to describe it, it would be change something, test everything. What we mean by that is that you have seen that we have a very complex library of components, and as we move with changes of software, of firmware, even hardware, all of these changes can produce unintended side effects that we need to protect from. And also, it largely increases chances to detect bugs. It's for sure an indispensable method in Typhoon HIL quality assurance. Specifically, the regression testing that you will see today is implemented as a batch unit testing. Now, this brings us to the fundamental tool that we are going to use, which is a Python programming language. Just so you know, entire Typhoon HIL software is written in Python. So it's natural for us to lean on Python for test automation as well. The language appeared in 1991, and it's interesting to know that for 5 times in a row, so between 2011 and 2016, it was voted #1 most popular coding language. And we'll see some of the reasons for that. So what is Python? It's a high-level object-oriented programming language that is kind of similar to MATLAB, Perl, or Java. It's used in a wide range of applications, and as I said, our entire software toolchain is written in Python. It's really easy to master as it uses clean and clear syntax. There are very few reserved keywords, and the code is extremely readable. It's highly portable and extensible, so there are many external libraries with very good community that supports them. Basically, there are over 38,000 third-party packages available. So let's see in some examples actually how it compares against other languages. So Python uses white space indentation rather than curly braces or keywords to delimit the blocks of code. That results in shorter, cleaner, and more readable code. So programmers usually end up liking it. And what is also great is that in Python, you don't have to specify variable type compared to C. And in this comparison of simple code, which basically executes the same, it's the same code, but it took us about 10 lines in C, while only 6, actually 13 lines in C and only 6 in Python. So when you write Python files, they're saved as .py, and you can run the code simply by double-clicking on the file, or you could run it from the command prompt. Also, you can use interactive environments, so basically integrated development environments. So you can type line by line, and it will immediately execute. With the installation of Typhoon HIL, you also get Python idle, which actually does this. And in addition to that, you need to know that we are installing Python 2.7, but we are aiming for transition to Python 3. Now, this is a very important part of our tool chain. Many people are beginners in programming languages, especially when they need to write tests. And we have a tool that can actually help you deal with not knowing our API and not being familiar with Python syntax, because this tool will actually convert GUI commands into a Python code. So it's a great way for beginners to get familiar with both our API and Python syntax. So this was a very brief information on Python. Of course, there are numerous tutorials on YouTube and other resources on the internet. A lot more could be said, but since we're actually talking about test automation, let's give some attention to some principles that we need to follow. So a test script actually consists of stimulus, data acquisition, data analysis, and results reporting. What do we mean by stimulus? Well, it's basically an input to our model or to our simulation. So in this case, if we have a model device under test, we are providing such input that are required to test the functionality that we define in the test scope. And the device under test can either be a controller or a HIL model of a power electronic device or a power system. So if we are talking about inputs to the controller, we're talking like initializing or stopping the controller, changing the power reference, maybe a speed reference of a machine controller, etc. And talking about a HIL model stimulus, we're talking about changing voltage of a voltage source, or maybe irradiance for if we have a PV panel inside our model, different load profiles, faults, etc. And remember that we can provide these stimulus at 1 microsecond precision. So very complex sequences can be generated by combining Python with our API, such as frequency sweep, low voltage write-through, dynamic MPPT, and various complex load profiles and harmonics situations. The test automation story does not begin in a standalone script writing, and it's actually present already in the HIL SCADA tool. And we will see how HIL SCADA already has some semi-automated testing capabilities. For fully automated and unsupervised testing, we will be using the script editor. And as I mentioned, there are special time commands that we can send to HIL and execute different stimulus at 1 simulation step precision. Data capture, well, we always need some minimum set of data in order to make a decision and finally create a report. Now, this data could either be available on HIL device or controller, depending on the test scope. A recommendation is that if the data exists on a HIL device or of both devices, you should always go for the HIL device because it's been optimized for avoidance of offset and scaling errors, as well as eliminating measurement noise and resolution loss. As far as data capture capabilities, we can do asynchronous read and of multiple signals, as well as deep memory capture. Depending on the HIL device used, we can capture up to 64 megasamples. So data analysis is closely tied to some libraries that exist in Python. We mentioned there are over 38,000 packages, but some very popular ones are the NumPy, SciPy, and Matplotlib. NumPy provides numerical computations as well as operations with different array and matrix types. SciPy is an excellent tool for signal processing, so many domain-specific toolboxes, as well as optimizations and statistics tools. The Matplotlib is a library that is used with PyPlot plotting framework, which in terms of 2D plotting gives a publication quality plots, and for 3D plotting you can also do some basic stuff. The report usually consists of either booleans or some detailed test logs, and you can as well save some waveforms just as a side information as an addition to a basic report. In terms of reporting options, it's also provided through third-party libraries, so there are tools like Sphinx that was used for official Python documentations. There are poly reports. In Typhoon, we use HTML, and we will see that today when we generate some regression testing reports. And we also use LibreOffice, which is used in Test Suite tool. And we can see some example here on the left of the HTML report and LibreOffice reports on the right. So this was an introductory presentation, and in the next one we learned some basic test automation, first semi-automated way in HIL SCADA, then we moved to our script editor tool, and we learned how to use API Wizard to write tests. Thanks for listening, and see you after the 15-minute break.
स्क्रिप्ट राइटिंग करवाएंगे ना
मुझे लग रहा है ऐसे ही बोला था ना
स्क्रिप्ट राइटिंग बोल
वही लिखा है ना सेम कमेंट सी है बट इसमें वो जो डिक्लेरेशन ऑफ लाइब्रेरी डिक्लेरेशन और लाइक इंटीजर डिक्लेरेशन वाला नहीं चाहिए डायरेक्टली बहुत कम लोग हैं
वही कहते हैं मैटलैब वाला बस सेम है मैटलैब की तरह
फिर उसकी खत्म ही हो गई चार्जर ना, as you were saying ना चार्जर नहीं लगा, इसकी बैटरी खत्म हो गई। लगा ही दो।
Hello again, and let's continue our discussion on test automation. We will learn first how to do some semi-automated testing in our HIL SCADA. For that, we're going to remind ourselves of an example, which is the grid-connected inverter example. You've seen it in our previous videos. So it consists of the three-phase inverter connected to grid, and also we have a fully implemented control in our signal processing. So I'm just going to point out some things. So in our control, we are able to send references for active and reactive power as SCADA inputs. And also what we're doing is we are measuring the powers by collecting the voltage and current pairs and then calculating here. I'm just pointing this out because we will be doing some tests that will investigate if our current controller is actually sending these references. I already have a pre-compiled model here, so my SCADA is already open. So I'm just going to play our simulation. If you remember, we were able to do some things like introduce different waveforms and faults. So we had this widget group for grid settings, which consists of grid waveform and grid impedance selector. So we could have changed from pure sine to harmonics. And now the question is, how was this implemented? Or for example, how did we implement the LVRT? So we could do an LVRT test and then inject this fault and observe the changes in the oscilloscope. Now, important thing to understand is that this is not hard-coded. This is actually fully programmable by you as a user. So let's actually look under the hood and how did we do this. So this widget here called grid waveform is actually a combo box widget that implements if-else statements that would normally be used in Python scripting language. So you see that we have defined some values here, which are pure sine and harmonics. On the other hand, we have the macro code in this editor box. And basically, if the input value of the combo box is pure sine, then we want something to happen. And that something is, we're saying to our HIL that it should set the source sine waveform without harmonics, so pure sine. This statement called elif is actually like saying else, but it's used when you have multiple if-else statements in Python. So if the value equals harmonics, then give me also an update of the sine waveform, but this time we're filling a list of harmonics with actual harmonics that are going to be applied. So we see that we have defined the order of harmonic, the percentage, the magnitude in percentage, as well as the angle can be defined. So this is fully changeable. Another example, we can check the fault type and inject fault. So fault type also is a combo box, but now we don't have much code going on here. Besides the mandatory imports, which we will talk about, we only have declaration that we have a fault type as global variable, and that equates to the input value from the bottom. By saying that this is a global variable, we are practically allowing the fault type widget to communicate with other widgets in terms of exchanging variables. So the fault type will communicate to inject fault macro, which is the basically a button widget that executes a macro on pressing the button. And then we can see that the fault type is actually used as a variable, although it's not defined in this space. And the same would be for the fault duration that we can see the code. So fault duration is in fact defined here, but it's also global. So that's how you make the possibility of exchanging variables inside within different widgets. There is also a central space for this called the panel initialization, where you can initialize certain variables, and then the whole SCADA panel has access to them, or you can even localize them within the specific widget group. So, for example, you can put these so this is in our next version, actually, that's coming next week. So even group widgets can have local namespace. Okay. Now you're probably wondering how can we actually know what to type when we are not familiar with Python syntax and we're not familiar with Typhoon API. Well, there's actually a very useful tool that you can access also in SCADA by pressing Edit in Code Editor. And this is the API wizard that basically contains all the objects inside the model, as you can see. We have the SCADA inputs, outputs, etc. And simply by defining, for example, what sort of voltage or frequency I want, and whether I want harmonics or not, I can just define it here visually and then transfer automatically as a code. And this is a huge time saver for beginners and a great way to learn how to both use Python and our API. Now, of course, this offers some test automation capability within SCADA, but still it's kind of semi-automated testing, as I said, because you still need to be here as an observer and change these combo boxes manually. You have to press buttons and so on. But it's actually possible to do this in a fully automated way. And for that, we need to switch to another tool called the script editor. So let's do that. Now you will notice that if I try to start script editor, I'll get a warning. The warning says that I have to close schematic editor and kill SCADA before running it. This is our system making sure that the same types of functions and Python modules will not be called simultaneously by the script editor and the regular tools such as schematic editor and kill SCADA. So whenever you see this, you should first close the SCADA as well as schematic editor. So I have it here, I need to close it. And only now, I should be able to open the script editor. As you can see, the environment is fairly simple. We have the script editor itself, where you write the code, and we have the console for receiving messages when the code executes. Here we have some toolbar, and important thing to understand is that even in this environment, we can use API Wizard. In fact, once you compile a schematic, it not only serves to run in HIL SCADA, but it's actually available for API Wizard. So it can generate this graphical user interface that you can later use to actually write some code without even knowing how to do it. Okay, so we will do some, as I mentioned, we will do something with our grid-connected converter model. And first things first, when you start writing scripts, you should import all the necessary libraries at the beginning. Since I already have a precompiled model, I don't need to open to use the opening of schematic in my code. I will simply load it to HIL, and I will be using virtual HIL, so I can define the path from where my model should come from. Here, I can say I want virtual HIL and press insert. Immediately, I'm getting 2 lines of code. First, the API HIL is imported. Now, this is a typical way of if you want to have a handler during your code writing. So we are saying import Typhoon API HIL as HIL, but it can be as anything. So it doesn't matter. This is just basically up to you. So then this handler is actually calling from our HIL API the load model function, and then those are the parameters that we define here, such as the path, and we are using the virtual HIL device, so virtual HIL device is true. And it's always nice to kind of put some comment before just to say what this specifically, what this code does. Okay, so next thing we need to do, we need to initialize our model settings. So think of it as the same. It is the same thing as if you were looking into a SCADA window. So once you've loaded the model, before you run it, you want to initialize. And by that, we will be initializing sources. So we have a DC link there, so that's a constant source, and it should be using about 800 volts. And we have the grid side, which is phase to ground 120 volts, and it was a 60 hertz model. So now I can initialize source, I can initialize grid. So actually, let's say initialize sources. Next, I want to initialize my controller. Specifically, I want to initialize active and reactive power settings. And where is our controller? Where we have SCADA inputs. So remember, we had those PREF, QREF references. And let's say that we will be working with a power factor of 1, so there won't be any reactive power in this case, but we will have 10 kilowatts of active. Okay. So we have initialized the controller. We need to, next thing we need to do is basically start the simulation. You can find that in another card, which says other commands. So let's say start simulation. I'll just try to make it more visible for you. And as you can see, there is a simple button to do this. And also we can print some message just to inform that we're starting simulation. And of course, you need to save your script before running it. So we're going to save it. So now that we've started the simulation, we want to provide the stimulus. This is our first test script element. So provide stimulus. The idea for today is to change the reference value of our controller and then measure active power to confirm that this change actually took place, that controller is indeed setting the desired reference. So we need to give a new set of commands. So we could either copy this piece of code and then change this value, but I'm actually going to, for the sake of our users, again, resort to API and to this SCADA input and just type here 30 kilowatts. They're expressed in watts, so that's why we're typing 30,000. And this is the stimulus. Now, next thing is the data acquisition. First, we will be running this script as we will be running the script and we will be reading the signals directly. So we will be reading power as an analog signal. So let's type data capture, and we won't be using capture right now, we will use it later, but other commands contains what we need, which is the read analog signal command. And then all of the signals that exist in the model are available to you. So we need P as that was the active power. So insert, and as simple as that, we have a HIL read analog signal. And then we are going to assign a variable to this one. We will say P measure equals P that is read as an analog signal. Okay, so next thing, we're going to analyze this captured data. I have a fairly simple idea in mind, which is to compare the P measured with PREF. So actually, here I need to also do that and declare 30,000 kilowatts, and then I can simply put PREF instead of the actual value. Always try to parameterize your model so that later it's easier to introduce changes throughout the code. Okay, so the idea is to check if the P measured is within some specified boundaries. So how am I going to do this? I'm going to check if P measured. So immediately I can choose it here. If it's lower than PREF, and then let's give it some tolerance of, let's say, 10 watts, or if P measure is higher than PREF plus 10 watts, so if this is true, then inform me that test has failed. And also, we actually might be interested in those values, so print PREF. First, you give the actual part that's going to be printed in quotations, and then you can simply, after a comma separation, you can type PREF, and it will be taken from the variable. The same thing goes for P measure. Okay, good. And of course, this is the case if the test failed, but we need to also specify what happens in another case by saying else, double colon, and we can just take this piece here and say print test cost. Okay, so far we have almost all the elements of the test script, and in fact this part here that prints is kind of a primitive way to report. So this will be printed in our console, so this is the first way of how you can make some very simple reporting. So this is actually data analysis and reporting. And finally, once we are happy with our test script, we want to stop the simulation. And this is also available in our API wizard as a command, and here it is. Okay, so we can try to run the script now and see how it works. I'm going to press play. So what's happening is we have HIL that is being detected. Okay, simulation start, test failed. Okay, so you can see that the P measured and P reference are quite different. Now the reason for that is that we actually executed the stimulus, but then immediately we went for data capture for reading analog signals. In other words, we didn't allow our controller or our power system to settle when this reference was provided. I'm just going to type additional print here that says simulation stop. So going back to our stimulus, once we've done this, we actually want to wait for some time for the system to settle. So as you can see in our API wizard, we have commands that allow us to say wait in seconds, wait in milliseconds. And let's say that we want to wait, let's try 100 milliseconds and see if this is sufficient. So here wait. And you can see that this weight that we introduced actually was sufficient to get the correct value. So obviously, we have some settling time, and it's difficult to assess this on the basis of just using the reading analog signal, because we have much more accurate way of doing this is by deep capture using HIL memory buffer. And you can see that this was practically done without me accessing to API documentation or reading anything auxiliary. The only knowledge I needed besides the API wizard is that I needed to know how to make these prints. And as you can see, the expression here was fairly simple, and it's quite intuitive. When you're using Python, even when you're not sure what the actual syntax is, but you do have some programming experience, just try to kind of type if or if not, and you will be surprised how you might get the right syntax right away. So I hope that this was useful for you to see how to write a very simple script. We will see each other in, I believe, half an hour break. So see you until then.
Workshop
just a short announcement, so that you can slowly get back to your seats and for the sessions to continue. So 2 or 3 more minutes. Thank you very much.
नीचे देखो हार्डवेयर लोग कहीं आ रहे हैं ये कौन सा चैनल है 1 है कि 2 है 1 वाला नीचे होगा इस पे देखो ये आज का चल रहा है ये कल वाला
अभी लिंक्स चलना शुरू कर दिया अपने प्राइवेट कर दिया पब्लिक कर दिया नहीं
वो 2 नहीं किए मैंने कल वाला पब्लिक है आज वाला मैंने ना एक दिन में फेसबुक पे चेक कर लिया वीडियो आता है ऐड आती है ये तो महीना हो गया कुछ भी लिंक ओपन करूं ये जरूर आता है नहीं फेसबुक कोई भी लिंक ओपन करूं
वही आर्टिफिशियल इंटेलिजेंस का वही
डेली मुझे याद दिलाता है कि आपने ये चेक किया
ये मॉलवेयर है
हाँ वो एड्स आती है ना फेसबुक पे वो ग्रोथ साइट पे ऑटोमेटिकली मैंने देख लिया महीना हो गया मैं कोई भी वेबसाइट ओपन करूंगी उससे ऐड आ जाएगी
registering utilization
क्या मीन बजट एस्टिमेट
ओके ये अभी 5-3 मीटर value utilization
डी मतलब बजट एस्टिमेट है
ये कुछ लिखा है information may be supplied original basis please forward attachment of the study system मास्टर ऑर्डर्स के लिए
17-18
ओके बजट इसमें क्यों इंक्लूड है
क्या क्या देना है इसमें
मास्टर ऑर्डर्स के लिए यूटिलाइजेशन बजट इसमें यूटिलाइजेशन है तो क्या यूटिलाइज किया है
नहीं दिया मैंने तो दिया नहीं
हमें इस टाइम क्या लिया है कि एक्सेस नहीं है फिर
एक्सेस नहीं है
परचेज नहीं किया
2017-18 तो ये वाला हो गया ना
इस साल में क्या
अनस्कैमर लिया
लिया सो ऊपर भेजने लगा वैल्यू ऑफ परचेज ऑर्डर प्लेस्ड डिलीवरी पेंडिंग ओके वैल्यू वो भी है से फिर ये भी है वैल्यू परचेज ऑर्डर प्लेस्ड डिलीवरी पेंडिंग फिर ये भी आंसर्स भी आएगा तो इसलिए उस लेडी को फोन करके बताओ कि ये बनाने के लिए देखो गया है क्या ऑफिस को लेडी को फॉरवर्ड कर दो इसको फॉरवर्ड करना जयंती
कि देखो ये आपको इसलिए आया क्योंकि हॉस्टल ऑर्डर मुझे नहीं आया इन्होंने सिर्फ एचओडीज को भेजा
ओके अभी किसको
ये लेडी नॉर्मल की जयंती को
दोनों को भेज देते को बोलो थोड़ा और भी रेस्पॉन्स भी करेंगे जयंती को बोलो असिस्ट फाइल लेके देखो दोनों के लिए
एनसीएस की फाइल आपके पास है
एनसीएस का फाइल उनके पास भी आ गया।
किन के पास?
वो तो मैं व्हाट्सएप पे कर देती हूँ, मेरे पास
ऑर्डर देखते हैं।
ऑर्डर है। मुझे बोलो कि शुरू में आंसर्स को हम आपको व्हाट्सएप में भेज रहे हैं, दूसरा आप उसका बनाने के लिए अर्जेंट है, अभी देना है, अभी 4 बजे।
हेलो, हाँ आपको ना शिवी मैम भेज दी थी मेल ऑलरेडी।
हाँ।
आपको जयंती मैडम दोनों को शिवी मैम ने एक मेल भेजी है, वो अर्जेंट है, डायरेक्टर ने बोला 3 बजे तक देना था। BE_ यूटिलाइजेशन, वो वर्ड फाइल खोलो, जल्दी से खोलो, मैं बताती हूँ क्या करना है।
आंसर्स को मैंने भेज दिया, बल्कि ऑनलाइन में
ये देख लेते हैं ना इसमें हमने क्या क्या आइडिया है। इसमें खोल लिया आपने?
यूटिलाइजेशन सर्टिफिकेट यूटिलाइजेशन हमने क्या यूटिलाइज किया, हमने तो
हाँ, इसमें लिखो जो नेम ऑफ डिपार्टमेंट, हमारा अमाउंट लिख के टोटल अमाउंट एज पर बजट एस्टिमेट क्या होगा, हमने कितना बजट दिया है। ये तो रिवाइज बजट है ना?
हाँ, रिवाइज बजट ही होगा।
रिवाइज बजट लिख के देना है कि
रिवाइज बजट यहाँ भी आपने जो दिया है।
मेरे यहाँ से तो बजट एस्टिमेट नहीं होना चाहिए पिछले साल का, रिवाइज बजट तो अभी तक अप्रूव ही नहीं हुआ, हम कैसे दे सकते हैं? सुनो, एक काम करती हूँ मैं, आती हूँ 1 बजे, ठीक है? ये नहीं, ये तो
Hello and welcome to continuation of our lecture on how to write test automation scripts using Typhoon HIL API wizard. Let's continue from where we left off and just make an overview of what we did. So we've done a fairly simple script that involved providing stimulus and then reading through read analog signal command. So we had only one instance of signal reading, which we then took into our analysis and reporting. But the question is how to get a continuous stream of data and how to then use that data to, for example, create some plots, etc. So for that, we are going to actually utilize the capture functionality of HIL device, and we will be directly accessing the memory buffer of HIL device. In our API wizard, there are basically 3 types of commands, and the capture commands are in the middle part. Let's open them up. So you have the ability to save captured signals to a particular folder, which I'm not interested in right now because I will be accessing directly from the script. I will be accessing the buffer. So I'm more interested in setting the capture and trigger signal. So the decimation 1 is fine with me. I'm just going to add more samples just to be sure. We will be capturing our power signal again. So first I need to select it here. Then I have it as my analog source to capture. And since the test script goes by first initializing the controller at 10 kilowatts and then raising to 30 kilowatts, my idea is to initialize this capture to actually trigger it with rising edge and with a threshold of 20 kilowatts. I won't be using any offsets, so we are actually ready to insert the capture command. Okay, we'll just make some comment here. Capture. So by pressing insert capture command, we are getting larger chunk of code, which would take us some time, both in terms of studying how to enter it and what to enter. So you can see that every piece of here was transferred into lines of code. So the capture, the false refers that we're not using digital but analog capture. And here are the trigger settings. So we're using power as an analog signal to trigger at rising edge at threshold of 20 kV. This is actually the channel that we're capturing. Now here is, so we are using regular Python list. So our capture data buffer is in the beginning an empty list. And this part here is not only referring to initialization, but the actual start of capture process is when you arm the trigger. And this final part here is basically an expression using while loop and this command capture in progress to kind of have the capture running while the simulation executes. So in order to make this work, we actually need to rearrange our old code a little bit. So before we can actually engage the capture process, I will need to move the simulation start before that. Because if you think of how we did it in SCADA, there's not much sense in arming the trigger if your simulation is first not running. And also providing the stimulus must be changed and put before we can say that capture is in progress. Because first we have the arming of the trigger and then the stimulus that will actually make capture in progress possible. And we can leave this all the data here. What we need to do now is also see how we're going to unpack the data from the buffer. So let's say unpack data. So we have signal names, the actual numeric values, and the time. And then that actually is all in our capture data buffer. And since capture data actually contains a list of signals, and we have only one list of channels, and we have only one channel here, so we are going to actually take our p-measured variable and assign it to capture data with index 0, because that is the beginning index when you are accessing lists. Okay, so now we have unpacked the data, but we still need to do some plotting. Before we plot, another import is necessary, and that is the matplotlib library that I spoke about in the presentation. So we are importing matplotlib of the pyplot as plt. Now we're ready for some plotting commands. So we will be plotting time axis, which is the axis, and we will be plotting P measured. And we might actually give it some color. Let's say that the color of the plotted signal is red. This is the expression how to do it. Next thing, we might make the plot more informative by adding some labels. So let's have some X label. That would be time expressed in seconds. And Y label, this is active power. Expressed in watts.
मैटलॉब का सेम ही है, एक जो है PLT डॉट करना है, इन द सेंस मैटलॉब का सिंटैक्स ही नॉर्मली यूज
Finally, I need to actually show plot on the screen. So I'm using show command. Of course, you see that now I'm not accessing API wizard anymore because Matplotlib is exclusively Python, not Typhoon HIL's library. So a little bit of knowledge is needed for that, but as I said, there is a quite good community that can support you in this. Since this command, plot show, will actually make a break during my script, I want to inform the user that he needs to take action to continue the script. So I'm going to add something that says close the plot window to proceed. Okay. I believe that we are ready to run this script. Let's see. So we're building virtual HIL again. And we have the command, and I have a prompt here that actually produces a figure. So you can see the script is running, but it's actually paused, and there is a message that says close the plot window to proceed. And let's have a look at the plot itself. So we can see that we have what we wanted in terms of plotting. So axis and power signal in red, and we can do different things in this environment, this plotting framework. So we can, for example, pan the axis. Now we can see that there was, in fact, an overshoot in the controller for a very brief moment, let's say 100 milliseconds, up to 100 milliseconds before it actually settled, which kind of fits into that case where when we ran the code for the first time without HIL waiting, we actually had a test fail. So if this was a real world controller, you might be concerned why it's doing like this. So that's why it's useful to use the capture and memory buffer of HIL to study the signal continuously. What else you can do is you can zoom in and have a look at the signal. You can move from between different views, and you can simply go back to the original view. You can reset it on clicking on the home icon. In addition to that, you can actually configure the subplot screen by changing some changing its size, and you can reset to the original state. Finally, you can save the figure in one of these formats, just to name a few. So it can be PNG, it could be PDF, or even vector graphics. So once I'm happy with this figure, I will simply close it as my message asked me to. And then the rest of the old code as we had will execute. So now we have seen actually how to use the capture functionality, how to use the HIL memory buffer, and how to do some simple plotting. We still haven't seen some more advanced reporting, which we will also see very soon. I see a question about the mandatory command section on the top of my screen. So we have basically two imports. One is actual API from Typhoon. So we are importing that as HIL. And the second one is the matplotlib, which is Python's built-in library. So all of this actually comes pre-installed when you install Typhoon HIL, and with it you get Python 2.7. Okay, so this was, we just used the API wizard to create a script and run an individual script. But now the question is, how do we proceed to batch testing? How do we run multiple scripts? And that is closely tied with the implementation of regression testing in Typhoon HIL. So for that purpose, I'm going to use some examples that actually come with your virtual HIL version that you can install for free. And I'm going to open one. So it is in our examples folder. So examples, scripts. There is a script called test executor. And I'm going to open, before I open it, just to comment on what we see here is that we have three folders that contain three separate tests for passive components such as for resistor, inductor, and capacitor. So each one is an individual test script. What is going to happen is the test executor will be accessing them one by one. So what you see here is a test executor script, and it's actually a separate module in the Typhoon's API. You can see the import here. What is typical for this test executor is that it can pass arguments to other scripts. So for example, we can say that whether we are using a true HIL or virtual HIL. So in our case, we were working with virtual HIL, and we are going to continue to do so. So we have to say true, and then select the preferred HIL device, and basically you type in the model, the I/O board revision, which is normally always 3, and finally you type in the firmware configuration. Basically, the first and the third number are always the most important ones. And here we have this command that actually builds a tuple containing each path to each of the test scripts. So we have a relative path. Just side information in Python, you can both use absolute and relative paths. And we have the arguments about whether virtual HIL device or HIL devices is used. If I press play, immediately I'm getting HTML window. So the test executor report is that HTML report that I was talking about. As you can see now, we don't have a detailed console log. But we have the information that the test has been started on a specific date and time. This is the first test that we are running, which is the resistor circuit test. And the status can be either in progress or can be passed, failed. The test can also return error if there was some problem with, for example, loading the HIL. And finally, you have this log column, which is like an individual log that you would normally find in console, but because we're running test executor, we don't see that in console. It's actually saved in the background. And this is, right now, this is a live test going on and being logged here. So if I were to refresh this page, you can see that I'm getting more data being loaded. So as you can see, we have iterations like test number 1, test number 2, test number 3, and so on. And after the execution of this test, we should see how the next test is being executed. And there we go. We can see now that basically we have a test of the inductor circuit. The first one passed, the next one is in progress. And this is much more advanced than simply having reports inside your console. As I said before, this is an indispensable tool in Typhoon HIL quality assurance testing. And normally when we run these tests, the test executor actually contains hundreds, if not thousands, of tests, something that for regression testing is quite essential, because without this approach, all of the unit testing, so component by component, would have to be done manually, which is very prone to error, not to mention the workforce that would have to do this manually. And while we are executing the test executor, just to mention that just because something is being executed, it doesn't mean that you cannot open next script. So, for example, I could open an individual script and have a look into it while this script is running. Of course, now I don't see the console, but I still have my reports running the third test, which is the capacitor test. Now, while this is finished, we can make some comments on more advanced tests that we have, that we didn't have a chance to cover in with the API executor at the API wizard. And you can see, for example, some structures such as this one here. So, for example, it says test, and then you have something in parentheses. Basically, this is known as a function, and these functions are written in such a way that you write test, and then you have to indent everything that belongs to that specific function. The great thing about functions is that they can be placed anywhere in the script. The order is not important as long as you make them callable, and usually functions end up at the end of the script so that the main body of the script is more readable. And they can be something quite as simple as printing, for example, this part here. which is the function called def print as begin, is just these 3 lines. But we are actually using print as begin in this section here. So that's why when you access some of these logs, you actually see that. So, for example, in the beginning, test begin. So try to make use of the function so that you make your code more readable. Okay, so this was the HTML report part. Tomorrow we will see even more advanced, like publication grade automatic report generation when we elaborate on the test suite tool. Okay, our test executor just finished. I just wanted to make some final comments for today regarding our API documentation. So you can access API help by pressing on this question mark button here. It's all in HTML, and it's easily accessible. We have let's say 6 main API modules referring to HIL itself, then the schematic editor. We even have the communication, like for Modbus API, test executor. For example, you could customize the test executor by replacing this with your logo, your title, and basically we have given you the roots for making your own test automation framework. And just one small comment. So you can search easily by, for example, looking at whatever you want. Maybe you are interested in machines, so you can just get anything like how to set machine torque or how to initialize machine. Let's say that you're interested how to initialize the machine speed, and then you get the command along with its description, arguments, what it returns, and where it's available. You have standalone scripts and macro scripts. And as well, you get an example for every command. So with this comment on the API documentation, we're going to wrap up for today. Tomorrow, we will talk about test suite, which is a combination of test automation and industry standards relating to grid connection and some other applications as well. Thanks for listening, and we will be doing some Q&A now, and goodbye for now.
क्वेश्चन आंसर करेंगे लेकिन ये रजिस्ट्री टेस्ट किया है इसने ये हार्डवेयर के साथ में
जब तक ये आ रहे हैं ना वो सेंटर्स कनेक्ट कर लेते हैं उनको जो इन्फॉर्मेशन देना है हम दे सकते हैं।
क्योंकि मैं कर रहा हूँ तो कर नहीं रहा
इसने तो कहीं बताया नहीं हार्डवेयर
और आगे
Hello, can you hear me?
Yeah, yes sir, we can hear you.
I can hear you also loud and clear. So how was the session today?
So it was really very useful. So today, like the coding also, Python coding also, because when we were early looking into it, it was big scripts there, and we were thinking, even participants here were thinking, oh God, how will we write these scripts? And at the back end, it is very tough. But today, he made it very simple. Say, like step by step, he showed like what are the scripts there. So now I think like after going through step by step, we'll also we understood like how to include all these libraries and what are the next steps. So it was a little really useful session today, and even the communication protocols and or because being electrical, I don't know, we are a little afraid of all these protocols, but still he made it little clear for us like how it goes on, and really the sessions were very useful. And I think now there are centers. Like centers, do you have? If you have any doubts, you can ask. Yes. Annamacharya Institute, Andhra Pradesh. Do you have any doubts?
Hello, ma'am.
Yeah. You want to ask something?
Yes, sir. Yes, ma'am. Hello.
Yes, please. Yes, we can hear you. Please ask.
Sir, regarding the any limitation on the size of the systems, sir? Number of buses. Sir, you have given certain licensed software. What is the limitation of the software? How many buses, etc.? Is it a full-fledged one or a limited one?
Yeah, so the license that you have now is called a virtual HIL 402 license, meaning whatever you can do on a 402, you can do in your current installation. As we mentioned yesterday, all of you who passed the certification will get unlimited license, meaning virtual 602, 604, virtual microgrid testbed. So you would have theoretical limitations of what is possible to be done in the HIL environment, meaning you will have limitations of the real-time environment. That's all. No limitations by means of license. Theoretically, the biggest system that our current technology can support comprises 16 604 devices, which translated to number of buses, I have to calculate this, it's 150 three-phase buses times 16 devices. This is the size of the network with 10 microsecond resolution that you can simulate. This is roughly speaking, of course.
Sir, another one, sir. Sir?
Yes?
Sir, you have, yesterday I asked you a question regarding for the reliability, sir. Please give out one of the example. Reliability indices. Hello?
Yes, yes, please.
Sir, yesterday I asked you regarding for the reliability indices. Can give out an example for determining the indices of the certain distribution network, etc.
I'm not sure that I can hear you properly.
Sir, I asked the question yesterday about the reliability
Yes.
indices of the system.
Yes, and we agreed that you will send a particular description of what you would like to see, and then we can prepare an example.
Sir, another one, sir, regarding the Python language script, can you able to give certain material regarding posted in the module, sir?
Yes, there are a couple of examples in the software installation. You can find them just by clicking open script, and you will immediately be in the folder examples, subfolder scripts. So there are scripts already there, a couple of simple examples, and one example for the test executor. So just go to the script editor and go to open script. You will immediately be in the folder examples/scripts where you have these few examples.
Thank you, sir.
Very welcome.
Institute.
Hello, ma'am.
Yeah.
IEC 61850 standard is possible for smart metering?
It is slower.
Is audible, ma'am?
Yes, it is audible, but it is slower.
Yeah, okay. IEC 61850 standard is possible for smart metering also?
Yeah, this is one of the protocols that we have on the development roadmap. Still not fully implemented, but will be shortly.
Okay, sir. Okay. Okay, thank you, sir.
Very welcome. Thank you for the questions.
The other center 20 number. It's over. Huh? Which center? The number 20 center, I think they have gone. Okay. So, I think all the centers have also asked the question, and some centers they were asking about some research project. That is, whenever what I understand is, say these softwares are available, but when we do research only, we come out with all these reliability index. Now you're asking, they are the research scopes. So anyway, Typhoon people are also there. Experts are there to help you out. You just send their data. So I think Rados and team can help you. But those are all, as we all know, it is research. So the research scholars have to come out, all the facilities, I think the software is having all the facilities. So we have to work on it and bring the new technology. And I think we can share it to them so that they will also appreciate it. And anyway, so thanks. It was a very wonderful session today. And apart from that, that's it. Here also the center, I don't think so. They are all satisfied with the lecture. And in the evening again, let them go and hear it again. So they will come out with more queries tomorrow.
Absolutely. Perfect. So once again, yes.
Okay. Sir, I think the second day, first day, your lectures are available in Moodle. The participants are saying your second day and third day, yesterday and day before yesterday, lectures are not available in the Moodle. So they want to go and see into it. So if you make it available, good.
Yes, we will do it immediately after this meeting. I think the videos are being converted as we speak. So they will be available in next 30 minutes or 1 hour. And then soon after that, also today's session is going to be there.
Yeah.
And this is all that you would need to pass the certification. All the topics that we will discuss tomorrow are some additional things that won't be a part of the certification process.
Okay.
Very good. Then thank you all very much one more time. Then we continue tomorrow same time. First, we will have one more informative session that we will cover some specifics like how we approach resonant converters, matrix converter applications, then some specific analysis like FFT, load flow, etc. Then we will also show you a special product developed by us called Test Suite, which is something that was built in the script editor environment that you learned today, which is a completely automated packaged test list or torrent of tests that converter manufacturer use to pre-certify their equipment against some very advanced grid codes. So tomorrow you will see also how this works, and then we will move to the certification part. I wish you luck also now, but we'll do that also tomorrow before the test. And that's it. Thank you all very much for today, and we continue tomorrow, and hopefully also in the days after tomorrow.
Yeah, thank you, sir. Thanks a lot. And for the centers, I have some announcement. Please, the centers, I have sent you the Excel sheet. Please send me the list of participants with correct spelling. If it is in capital, it will be good. For the participation certificate from where, like Knitter and Typhoon, the participation certificate all will be getting. So please send me the list. And I have sent you the feedback form also. I just want each and every participant to fill it and send me the hard copy of the feedback form to Knitter. Okay, and apart from that, I've told the coordinator and the co-coordinator will be getting money. So that also I've sent you the mail. Please send me the receipt also. But and all the attendance sheets. I think every day you're taking the attendance. Those who are attending, you're taking the attendance. So at the end of the day, that is tomorrow evening, I should get the scanned copy of all the attendance. Apart from that, you have to send me the hard copy with the feedback form and the receipt by Monday. By Monday or next week, you can do it. Okay. So that's it. And with tomorrow, we will meet at 1 o'clock. Okay. Thank you. Thank you, sir.
Thank you.